Welcome to section 1.2, types of graphs in R3. The purpose of this section is to give you a little introduction to the graphs of space curves and surfaces that we're going to be studying later in the course. So let's start with 1.2.1 space curves. So in the very next chapter, we're going to see that a vector valued function is a function of a real variable t that yields a vector, something of the form r of t. Notice that r of t has a little vector symbol on it, is f1 of t, f2 of t, and f3 of t, all within a vector, where f1, f2, and f3 are real valued functions. And if these functions f1, f2, f3 are continuous, then the graph of r of t is called a space curve or a vector curve. So for example, the graph of a space curve might look something like this. Like a piece of string floating in space, the vector r would be the position vector of any point on that curve. So r of t links points on that curve to the origin. And space curves are one-dimensional objects. And you've already seen an example of a space curve in your linear course, of course. A line, a straight curve. Let's go and take a quick look at surfaces then. So surfaces are two-dimensional geometric objects in three-dimensional space, and they can be grouped into two categories, those that are graphs of functions and those that are not. So functions, a function of two variables is a rule that assigns at most one real number z to each pair of real numbers x and y, and we write z is equal to f of xy. The graph of a function is a surface. For example, a function's graph might look something like this. So this looks maybe a little familiar. This might remind you of something that you've seen in linear, but is a little curvy. The idea here is that for any point down in the xy plane, so this is xy0, but we think of this as being in the domain, so we think about this as just a point xy, although strictly speaking in three-dimensional space it's xy and 0. This point maps up to a point on the function surface, and the coordinates of that point would be x, y, and z, where z is calculated as a function of these two input values, x and y. Of course, you've already seen something like this in your linear algebra course, planes. Of course, they are flat surfaces, they're not curvy, but strictly speaking, not all planes are functions. So you've seen the general equation ax plus by plus cz is equal to d. You need the c value to not be 0 for a plane to be a function. Functions pass the vertical line test. That's something that might sound familiar to you. The vertical line test, which says that any vertical line cuts the graph of a function at most once, right? So it doesn't necessarily need to cut, but if it does cut the graph of a function, it'll cut it at most one time if it's the graph of a function. So it cuts the graph at most once. You might remember a very similar rule from high school. Not all function graphs, or sorry, not all surfaces are function graphs. Not all surfaces pass the vertical line test. For example, here's one that doesn't. We're going to be studying both kinds of surfaces. So this, which you might remember from Cal 2, looks like a volume of revolution. It doesn't need to be. In Cal 3, it can be a surface in and of itself. And surfaces of this type, you see, don't pass the vertical line test. So a vertical line here, you see, cuts the graph in two places. Surfaces of this type are often the graph of an equation of the form f of x, y, z is equal to k. That's something that we're going to study in a later chapter where k is just a real number. So in the next section, we'll go along and study a specific type of surface called a cylinder.